Imagine you're about to plaster a wall, but the sand you're using is full of impurities. You need a sieve that blocks the debris and lets only the fine sand through. If the mesh is too wide, the dirt gets through. If it's too tight, even the good sand is blocked. Designing a filter works the same way. You decide what stays out and what gets through, and this logic applies perfectly to electrical signals too. The Fourier Transform is the tool that reveals the noise hiding inside a signal. It takes the signal from the time domain into the frequency domain, like flipping on a light to see what's really going on. It's like using a magnifying glass to spot the unwanted stuff mixed in. If you're serious about designing filters, understanding the Fourier Transform is a must. In this example, we see a sine wave in the time domain, and just below it its frequency domain representation, obtained using the Fourier Transform. This kind of analysis is typically done with oscilloscopes or specialized software. Notice that the signal is made up of several frequency components. Starting around 50 Hz, one of them stands out. It has the highest amplitude, highlighted by the arrow. Designing a filter is basically about choosing a window, a range of frequencies you want to keep. This choice is defined by the cutoff frequency, which marks the point where the signal starts to fade out. In practice, it's the frequency where the output drops to about 70% of the input, meaning the signal's power is cut in half. That's the first step in filter design, determining the cutoff frequency. Let's look at a practical example. An active low-pass filter using an operational amplifier as shown in the diagram. Based on the transfer function, we can see that the cutoff frequency depends on the resistor RF and the capacitor. By adjusting these components, we control the filter's passband. The gain in the passband is determined by the ratio between RF and RI. This means we can first set the cutoff frequency and then calculate RI to achieve the desired gain. That's the core concept behind designing active filters. In this example, let's consider a cutoff frequency of 120 Hz. We set the capacitor to 1 microfarad. With that, we can directly calculate the resistor RF, which comes out to approximately 1.3 k ohms. Now, if we want a unity gain, we just need to make RF equal to RI, since the gain is determined by their ratio. And there we have it, a simple active low-pass filter tuned for both frequency and gain. By simulating the circuit in appropriate software, using the calculated resistor and capacitor values, we can observe the signals. The green trace is the input, and the purple trace is the output. Notice that the input signal has an amplitude of 10 volts. At the cutoff frequency around 120 Hz, the output drops to 7.09 volts. That's the expected 30% attenuation. Also, pay attention to the phase shift between the signals. This happens because we're using an inverting op-amp configuration. Understanding the details we covered in this video is essential for moving forward in your study of filters. There are many other important aspects that go beyond what we discussed here, like choosing the right topology, defining transition bands, determining the filter order, and understanding the differences between active and passive filters. If you need help or want to dive deeper into the topic, feel free to reach out. We're here to support your learning journey.